Let's work on estimating a parameter average given a sample average. This is going to be remarkably similar to estimating a parameter proportion. We're just going to have to change some things around. We're going to have to use a different standard deviation and a different critical value. We won't use z-scores, we'll be using t-scores. But let's proceed. At a local hospital, we find 15 newborns with an average weight of 30.9 hectograms. In fact, let's go ahead and give that a name. The average of our sample is 30.9 hectograms. The standard deviation of our sample is 2.9 hectograms. And how certain do we want to be? We want to estimate the true average of newborns with 90% accuracy. Okay, so we're going to proceed in the exact same manner that we did with proportions. We're going to draw a distribution. And at the center of this distribution, because we're trying to estimate a population parameter, we're going to center it at our sample statistic, our best guess, 30.9 hectograms. Okay, and we want to be 90% sure. So we want to move to the left and to the right by some margin of error until we collect 90% of our probability, which means that we have 5% probability in that tail and 5% probability in that tail. Now, what is this E, margin of error? Again, by a rearrangement of your z-score equation, you can find that error is equal to z times standard deviation, except again, this is averages, not proportions. So we are going to use t-scores as a critical value, not z. And our standard deviation by the central limit theorem, because we're dealing with averages, this is our sample standard deviation divided by the square root of n, right? That's given to us by the central limit theorem. So let's worry about the t-score here in a minute, because we already know our sample standard deviation. That was 2.9. We also know how many newborns we're taking an average of. We took an average of 15 newborns. Okay. Now this t-score. So just like we did with proportions, we're going to look at the picture, and that is going to tell us what t-score we need. So note, I have 90% in the middle and 5% in both of my tails, or rather 5% in each of my tails. So let's find which critical value we need. Now, again, this is not a proportion. So we are not going to be using z-scores. We are going to be using t-scores. But as long as you have that picture drawn, you're going to choose the right one. So notice here, as I go down the column, I'm looking at degrees of freedom, not sample size. So my sample size was 15, meaning my degrees of freedom is one less than that. We're looking at 14. Now, which column should we pick? Well, look here. How much probability do we have in one of the tails? If we go back to the picture, each tail has 5% probability, right? There's 5% in that one tail, and there's 5% in this one tail. So the one tail, we're looking for 5% right there. Or you can think of that picture another way. You've got 10% in both of the tails, right? It means the exact same thing. Or you can think about it as another way. It's the cumulative probability of 95%, right? If I go back to my picture, oh, I keep doing that. If I go back to my picture and look for that critical value right there, how much area is to the left of it? 95. But either way, we're looking at this column. So our critical value that we need is 1.761. That's the critical value that matches our picture. So when you go through this, you find a margin of error of 1.3186. And if you move that margin of error to the left and to the right, your lower bound on your 90% confidence interval is 29.58 hectograms, And your upper bound is 32.22 hectograms. So this 32.22 goes right there. This 29.58 is the lower bound. So you're 90% sure that the true average weight of newborns based on your sample is between 29.58 hectograms and 32.22 hectograms.